Hello everyone, my name is Biruk Sara. I'm a PhD student at Qataiyat University of Marrakesh. I'm so honored to present to you my research study entitled A Multimodal Route Recommendation Framework Based on Urban Congestion Management, a work that I accomplished in collaboration with my supervisors Abdelaziz Al-Faziqi and Mohammed Sidgar. The following outlines will be addressed: general context, introduction, the multimodal route recommendation process, the multimodal network modeling, the congestion computing method, the optimal pathfinding algorithm, the experimental results, and finally the conclusion and perspectives. Our research study fits into the context of road network policies that consist mainly on optimizing network operations to manage congestion impacts, considering multiple impacts through relocating road space, managing traffic to improve safety, business activity, and neighborhood livability. The phenomenon of congestion has no unified definition. In urban settings, it is more related to the experience of the road user. It represents the difference between users' expectations of the road network and how it actually performs. It is the level at which the transportation system performance is no longer acceptable due to traffic interference. Congestion is harmful as it impacts travel times and increases emissions. Slower moving vehicles can be helpful to reduce congestion impacts. Vehicle congestion should be managed because it negatively affects urban areas and the economy. Our motivation consists mainly on defining, measuring, and addressing the traffic congestion problem using innovative solutions. The main goal is to focus on the predictability and reliability by improving monitoring of traffic conditions and trends, improving road safety, ensuring a smart and efficient transportation system, coordinating street use, prioritizing people and good movements. The proposed solution is a multimodal route recommendation framework that uses traffic and transit data, quantifies the traffic congestion using congestion measures and indicators, finds the optimal least congested multimodal path using any label setting algorithm such as the Dijkstra algorithm, optimizes the traffic flow by providing to road users relevant multimodal path recommendations. The main steps of the route recommendation process are the use of the traffic and transit data and the multimodal road network data in order to generate the multi-layered graph and compute the traffic congestion indexes. Associating these two, we will obtain a weighted multi-layer graph to finally apply the proposed optimal path-finding algorithm and provide recommendation about the least congested path to make a journey. Several components are considered in the multimodal road network modeling such as driving, walking, parking the car, waiting at a bus stop, and using the car. To represent all these components, the network structure will consist of 3 monomodal layers, as you can see in the figure, interconnected together to form a multi-layer graph. Each layer represents a different transport mode: car, walking, and bus. Each node in the graph is a road intersection, a bus station, or a bus stop. Edges represent either a segment between 2 bus stops in the bus layer or a segment between 2 intersections having similar properties in the car and walking modes. Transition nodes do not belong to any layer and represent parking spaces either on street area or car parks. These nodes makes it possible to alternate from or to a car mode. The weights associated to each edge are time independent for walking modes, considering that it is not affected by the congestion level, time dependent for the car and bus modes, and are computed for each segment based on multiple parameters that changes periodically. The proposed weight function computation method is detailed next. This method uses more than one indicator to provide a better and true evaluation of the congestion state. The 3 measures are the volume to capacity ratio, which is the ratio between the count of the vehicle passing through segment E and the maximum number of vehicles that can support that segment. The load speed rate, which is the ratio between the travel time spent at very low speed and the total travel time, both associated to the same road segment. And we have the third measure, which is the decreased speed rate, it reflects the rate of the reduced speed of the vehicle passing through a segment due to congested situation. These measures are calculated separately based on the simulated traffic and transit data and are combined into one measure, which is the congestion index represented in the last formula. The combination of these three measures give a preview of the congestion state while taking into consideration changes in speed while traveling, the passenger's sense of annoyance and displeasure by considering the volume to capacity ratio, as well as making use of the vehicle speed variation. Finding optimal paths in a weighted multilayer graph is in another way finding the shortest feasible paths between a departure point and an end point. It is a combination of the different nature of the cost of using those particular road segments. For the car driving mode, the weights are based on the congestion index, the segment length, and the delay at both intersections. For the bus mode, the weights are based on the congestion indexes, the segment length, the delay, and the average bus stop at both intersections. For the walk-in mode, the weights are calculated based on travel time required to cross a particular segment. The proposed algorithm in this study focuses on finding the one-way multimodal shortest path to travel between a start and end point. This figure illustrates the final state automaton that defines the possible mode combinations. A feasible multimodal path can be distinguished by several conditions that differ according to the final node. The conditions can range from car accessible, driving a car, and car inaccessible. Any label setting algorithm can be applied to the resulting weighted graph. In this work, we applied the Dijkstra algorithm. To validate our system, we ought to simulate the traffic and transit data, and we used a reduced map of Marrakech City for the testing scenario. The display table shows an example of the congestion indexes generation for some segments of the car network. The simulated traffic data for the car mode contains the distance between consecutive intersections, the capacity of the segment, travel time, delay time, travel counts are all required for the computing of the independent congestion measures, which are the volume to capacity ratio, the low speed rate, and the decreased speed rate. The measures are computed for each link using the aforementioned equations. The resulting congestion indexes are obtained in the last column. An example of the test request is illustrated in the following figure. The user is supposed to make the journey from the point O to point D, using both car and bus modes. Once the request is launched, the framework generates the graph that represents the surrounding area and calculates or updates the congestion indexes that represent the cost of the graph segments. For each segment of the generated multimodal graph, the weights are computed differently depending on the mode of transport it belongs to. The proposed algorithm for optimal path finding in the multimodal transportation network is then applied to generate an optimal trajectory recommendation while considering the transport mode selected by the user. An example of the resulting shortest path is presented in the following table. To conclude, our contribution consists on traffic and transit data simulation for the validation of the proposed framework, modeling the multimodal road network and the generation of the multi-layered graph, the calculation of the congestion index for each transportation mode, and the association of the congestion indexes with the road segments, application of the optimal path-finding algorithm, and the generation of the multimodal path recommendations. The major limitation of this study is the lack of real-world data. The route recommendation also can take into account additional data such as road deterioration, the location of traffic lights, etc. More beneficial recommendation will take into consideration other parameters besides the computer congestion indexes. As a perspective, we will take into consideration the user preferences data, the adaptation as well as the adaptation of the proposed algorithm to answer the two-way multimodal route recommendation problem. Thank you for your attention.